So now that we have some definitions of some points, lines, planes, rays, and things like that, now we can put them together to start get some more interesting geometry going on. And this is exactly what the Greeks did. They started to define angles and segments and things that we call postulates. Postulates are things that are just true about how these line segments and angles work together. And once we get postulates, we can make more interesting shapes and discover more interesting things called theorems that we can prove are true. But let's not get too far ahead of ourselves. Let's just start with some postulates. What happens when we put a couple segments or a couple rays or lines together? And how can we use these postulates that we discover with these? Let's check it out. So we have this concept of a segment that is just a piece of a line. And so the first thing we got to do is we got to figure out how we want to measure that. And so the way that the Greeks said we want to measure these line segments is they said, well, let's put this on a ruler. Let's imagine we had a ruler that had some marks on it here, and we want to find the distance between these 2 points. Well, think about it with me for a moment here. If we have, well, let's look down here, okay, at this example. If we have 2 points, and this point is at, that looks like 5.5. We'll round it off there, okay? That's at about 5.5 inches, and this little one's at 2 inches. Well, or centimeters, actually, it looks like it is. So what is the distance between those two points there? Well, we can pretty clearly see that it's, what, 3.5 jumps. 3.5. Well, what can we do with these two numbers? Well, we can subtract them, right? So 5.5 minus 2 is 3. Actually, 3.5, yeah? All right, so that's 3.5 centimeters. Well, that's nice. But what if we just say, take two numbers and what if we accidentally flip them around here? What if we make this 2 minus 3.5, or 2 minus 5.5, that is? So 2 minus 5.5, that's going to give us negative 3.5. Does it make any sense to say that that line segment is negative 3.5 centimeters long? No, we don't have negative lengths. We want to keep those lengths positive. Keep it positive here, all right? And so how do we make something positive? Do you remember from algebra what we used to make things positive? We had this little thing called an absolute value, all right? So if we take the absolute value, then that's going to take the absolute value of negative 3.5, which is positive 3.5. All right? So absolute value makes it positive. So that's our postulate there. All right? So we can say that if we have 2 points on a line that match up with the real numbers on a number line, okay, then we call that number the coordinate of the point. It's a location. We're familiar with coordinates. And if we want to find out how far 2 points are apart, we call that the distance, and we write it like this, AB. Notice there's no bar over it. So the name of this thing right here is line segment AB with a bar. That's its name. Its name has a little hat, a little bar over it there, all right? But when we don't have a bar right there, this means the length of AB. Very important. We're going to see that a lot. Okay, so this is the length of AB. So if we have a line segment with a bar over it like this, that's the name of it. Without a bar, that means we're finding the length. And the way we find its length is what we just kind of discovered there, is we want to subtract the coordinates and take the absolute value. All right? So that's the first postulate, ruler postulate. What about this guy? Got a point at 1. And I got a point at, what is this, 4.8 maybe? Okay. Well, we can subtract those. Wait a minute, that's negative 3.8. Well, we're going to take the absolute value, and it's just 3.8. Okay. So that's our first little postulate. Subtract and find the lengths. And then when we're talking about segments, we're going to be really interested in segments that are the same length. We like things to be the same length. And the name that we're going to use for the same length, The term that is congruent segments. So two segments that have the same length are congruent. Okay, so if we can say that AB is equal in length to CD, these two line segments are the same length, we say they're congruent. And the symbol for congruent is this little guy, a little equal sign with this little squiggly over it. So when we say this, now a little typo here, let's fix this up. We actually never want to say this. This right now is a statement that we can't say. The lengths are equal, that's true, but this is not the length. This is the name because it has its hat on. So we're going to erase that. And now it's a proper statement here. The length of AB is equal to the length of CD. Okay, lengths are equal. So is equal to is what we're going for here, all right? So that's an equal statement, nothing terribly new with that symbol, but that's the same as saying AB with a hat over it, with a bar over it, is congruent to CD. So this is the statement congruent. So congruent means the same length. You'll probably say that word about 500 times during the semester. All right, at least I will. All right, so the same length is congruent. So if we take some points here, we've got some points, what, -3, 4, that's J, and we've got 2, 4, that's K, and 1, 3, that's L, and 1, -2, that's M. And let's make some line segments here. So if we make the line segments J, K, and LM, we get those. Are those the same length? Well, we can kind of count spaces here. Looks like this one is 5, and this one is also 5. So, yep, they are the same length. So we can say that JK is congruent to LM. Segment JK is congruent to segment LM. All right? So, segments have length. We can find their length. We can say if they're congruent. All right, and we can also add segments together. Now, these are, let me remind you, these are postulates. Postulates are pretty basic things that are almost so obvious we don't have to say them, but it is important to say them, okay? So we've talked about this word collinear. Collinear means on the same line. So here we have 3 points that are not collinear. They're not in line. They're not on the same line. But here, B is in between A and C, so this is collinear. These guys are collinear. Now, if I were to tell you that this length from A to B is 5, maybe 5 centimeters, and this is 2 centimeters, then how long is it from A to C? If you were to walk, if you were an ant and you were to walk from here all the way over to C, well, isn't it pretty logical that it would be 7 units long? Yeah. Well, if this distance right here was 5 and this looks more like 4, does that mean that this distance from D to F is 9? Not really. Okay? Because if it's 5 over here and then 4, this is going to be a little shorter, right? Okay. So, if we have B in between A and C, like we did here, so it's in between or it's on the line, then we can say this distance, AB, and this distance, BC, the distance from B to C, add up to the whole distance, AC. And that's our postulate. So the two pieces add up to the whole. That's the key. And we can flip that around. If we know that the two pieces add up to the whole, then it must be between or collinear. In other words, on the same line, all right? So that about wraps up with line segments for now. Now we're going to put two line segments together and make an angle. And I just want to quickly go over how to name an angle, because we've got to be able to talk about things. So when we have an angle, most of us are familiar with angles. We've got two different rays. These rays are connected at a point. And that makes an angle. That end point there is called the vertex. So every angle has a vertex, and the rays are the sides of the angle there, all right? So it has a vertex and it has sides. All right, so you can name angles in a few different ways. You can use its vertex. So we could say that this guy right here is angle A. And we're always going to use this angle symbol, a little alligator mouth looking thing. This is the angle A. We can use a point on each side and its vertex. Okay, so we could use a point on the sides and the vertex. That would work. All right, so we could say this is angle CAB. That's another way to name the same angle. This thing could also be called angle CAB. It's kind of like, you know, my friends know me as Al, but my parents, like when my mom, when I get in trouble and my mom calls me, she says, "Hey, Caleb Al Bailey, get over here." That's like the full name, and that's just like a shortcut, okay? And we'll see times when we need one, not the other. We can also use a number sometimes, and that makes things a little easier for us, like this little number 1 here, and we could call this angle 1. So there's 3 ways to name this particular angle. Whoops, that's not going to work. Angle A, angle CAB, and angle 1. Those are all 3 names for this, okay? Here, your friends call me Al. My mom calls me Caleb Al Bailey. And when I'm on the soccer team, I'm angle number 1, all right? So just different names for the same angle, all right? So if we're looking for different names here, think about that. We got angle Q. We could call that angle PQR. Or we could flip that around. The order doesn't matter. We could call that RQP. That works also. Okay. Here, we've got a whole bunch of angles going on here. We've got the 2 angles. We've got angle 6. This is angle 6 right there. So angle 6, which is also angle SVR. Okay, that's the same angle. And what's another angle? How about the big angle? We could talk about this big angle here. We could say angle SVQ. That would also work. And we could have angle 5 and a bunch of other angles. Okay, we're going to leave it there. That's good enough. So we're talking about line segments, how we name them, how we find their lengths, and notice if they're congruent or not, and angles, and how we put them all together. So, all right, we'll go from there. And now we can start to put these together to find some interesting properties of angles, segments, and then even polygons, and on from there.